Hello, physics students. Today I want to look at the behavior of springs, specifically how springs relate to elastic potential energy. But here I'm using the PhET simulation, which you can find in our resources, or you can just search for phet.colorado.edu is where they're located. And I have two ideal springs, that is no energy lost to friction. And they're starting with the same spring constant, that is the same stiffness constant. K1 and K2 are equal. There's nothing magic about K. It's just a measure of how difficult it is to stretch the spring. It has to be measured. It can't be calculated from any sort of first principles. Now, since these springs are identical, I put the same mass pulling down. That is, I have the same force of gravity pulling down on these springs. Both these springs have shifted, about 11 centimeters down from the initial position, which I set to the top of the ruler. Now, if I put more weight on a spring, you'll see that the spring stretches a further distance, even though they have the same spring constant. Now, this is summarized by what is known as Hooke's law. Hooke's law says that the force on a spring is always equal to minus K times the spring constant times the distance you actually stretch the spring. That is, right now, I have a force of gravity pulling down on the spring, and the force pulling up on the spring force, is equal to minus kx. Now, the reason of that negative sign is it just means it's opposite the direction of the stretch, x. X stretched down in the negative direction, the spring force is pulling up in the positive direction. So, there you go. Now, if I change, right now these have identical spring constants, but the simulation allows me to actually change the spring constant. If I make the spring stiffer, you will see it doesn't need to stretch as far, and the mass will move up, and it doesn't need to stretch as far. However, if I make the spring less stiff, if I have a very small constant, right, you'll see that the mass stretches further down. And again, this is a little bit, let me change the mass out to the same mass on each side. So here you go. So on the left now, this first spring has a small spring constant, so it needs to stretch more than the other spring, which has a larger spring constant. And if I make this larger spring constant larger still, you see it stretches much less than the original amount. Okay, so that's generally the idea behind springs. So next, let's take a look at how springs work with energy. Okay, so now I'm going to set I have a spring here, some spring constant, and I have a mass I can set on the spring. And now what I've done is I have an energy graph shown here that will give us a live measure of the kinetic energy of the mass, the gravitational potential energy of the mass, and the elastic potential energy of the mass. Now, I've set damping to none. Damping in the current term of spring means internal friction. If dampening was on, then there would be internal friction, and I would lose energy to friction, which would turn the mechanical energy into heat. So let's start by also note that here the height 0 is set to the bottom of the simulation. So I'm going to hang the mass on this spring. This red dotted line just represents where the spring is naturally without any force on it. And notice that as I put the mass on the spring, I am changing my energy values. So as I pull down on the mass, you'll notice that the dark blue bar, the gravitational potential energy, becomes smaller. If I drag this all the way down, well, it won't let me. So if I drag it down here, I have very little potential energy stored in gravity, but the elastic potential energy is large. That's the lighter blue. Notice, take a note of the total energy off to the energy bars to the left. Now I'm going to let it go, and that's going to cause the mass to move, and we will see that we will then be converting some of this potential energy to kinetic energy. Now let's slow down the simulation, and over here to the left you can see what's happening. That, notice the total energy bar never changes. That's because there is no friction present. Also, I never convert all the potential energy into kinetic energy because this potential energy is a mix of both the gravitational potential energy and the elastic potential energy. In fact, the best I can do is convert the potential energy, kinetic energy. The best I get is when the elastic potential energy is stored is 0. Now, so that's the general idea. So the total energy doesn't change. I am moving back and forth between converting some of the potential energy into kinetic energy. But it's a little bit more complicated than just gravitational. As I drop lower, I'm decreasing my gravitational potential energy, but at the same time I'm increasing the potential energy of the spring. Now, the energy stored in the spring, the elastic potential energy, is equal to 1/2 the spring constant K times the stretch of the spring squared. That would be the stretch as measured from this dotted line, which I had set when the string was not stretched at all. All right, now just for curiosity, let's turn on damping. And when I turn on damping, you'll see another energy bar, a thermal energy bar will engage. That represents the energy loss because some of this mechanical energy will be converted into heat energy. That is, the spring will get warmer over time. You'll also see that the amplitude of the motion, how far the mass moves, will decrease. So let's turn this on. And there you go. So notice that every time the string stretches, I lose a little energy to friction, to damping, and this red energy bar still gets higher and higher. The blue bars over here on the total energy represents the available mechanical energy. Eventually, though, this will come to a stop, and then the kinetic energy has gone to 0. I've lost some of that total energy has been lost to heat. I still have some stretch of the spring, so I still have some elastic potential energy, and I am not at the lowest point of the table, so I still have some gravitational potential energy. So the interesting thing is what this looks like graphically. So let's move over to the notes and take a look at how this looks and where this equation actually comes from. Well, here I've set up an axis so we can graph what is happening with the force of the spring. So down here I have, we'll work horizontally so we don't need to work about gravity acting on it. So we just have an individual pulling on the spring. So if I don't pull on the spring by itself just has some natural length and I'm not pulling at all. So the resting length of the spring represents a pulling distance of 0. But if I pull on the spring to the right, the further I pull the spring, the more the spring will pull back. And I have the force of the spring pulling back. And remember, by Hooke's law, the force exerted by a spring will always be in the opposite direction of the direction of the pull. So if I don't pull on the spring at all, then the spring will have no force. As I pull more and more to the right, the size of the force of the spring will get larger and larger. So if I graph that, it's going to look like this. So notice that I'm going to be stretching my spring until I get to whatever the maximum force is here. So this would have a value of K times X, where I'm taking the absolute value so I can just see the size of the spring. Now, interestingly, the slope of this line is going to be equal to the force of the spring divided by the displacement X. That is, the slope of the line is going to be equal to the force of spring divided by X, which is going to give me the constant K. So the slope of this line must be equal to the spring constant K. Now, it's worth comparing it to what the case where if I was just pushing a cart at a constant force to the right. So if I push here this wagon with some force F and I push a distance where I'm just replacing the letter D with the letter X, in this case, what would my force graph look like? Well, in this case, my graph would look just like that, a constant force going a constant distance, x. Now, it's interesting to note here that, remember our equation for work. Work was equal to force times the distance force parallel times the distance d. Well, in this picture right here, the force is just the height of this box. And the distance d is simply my change in distance here. So if I multiply these two things together, what I'm really calculating is the area below the force line. So the first thing to note is that if I have a force distance graph, the work is equal to the area under the graph. And we note that work is the area of a force distance graph. Well, that's true and trivial for a constant force. However, that means that I have the ability now to calculate the work being done by a force that's changing. The problem with this work equation is it doesn't tell us what to do if my force is not a constant value. On a spring, the force is always changing value as my d increases. That is represented by this graph. But I can still apply the same rule, and I can calculate the area under this graph to calculate the work being done. Now, technically in calculus, this would be called doing an integral over an integral across the x. In calculus, if I poof this, and remember, my poof operator is an indication that calculus is being done behind the scenes. In calculus, I would say that the work done is equal to the integral of the force times the change in distance. In most first-year physics high school classes or in AP Physics 1, an algebra-based college class, we would not necessarily do this integration. But we have done areas under curves before. Remember when we talked about motion, the area under a velocity time graph was equal to the displacement. Now, this is a force distance graph, and I have that the area being done is equal to the work, or the change in energy added to an object. In this case, it would be the change of energy added to the spring. So this area is going to be equal to the potential energy stored in the spring. And well, this is just a triangle, and I know how to calculate the triangle. The area of a triangle is equal to 1/2 base times height. All right, so that one means that the area of this triangle is going to be equal to, the area is equal to 1/2 the force of the spring times the distance x. But again, this is 1/2 k times x. And so I get that the area of this force distance graph is equal to 1/2 kx squared. And that is, in fact, where the equation comes from for elastic potential energy. But it doesn't hold true just for a spring. Any changing force acting over a distance can be handled the same way. Even if this force was a big squiggly line, if I can calculate the area under that big squiggly line, as long as this is a force distance graph, that would be equal to the work being done. So to summarize, the big idea here is the area under any force distance graph is equal to work. And with all the repercussions, that means if it equals work, it equals the change of energy of an object. That change of energy could be going into kinetic energy, and I could take this area and set it equal to 1/2 mass times velocity squared. But that's the big idea here. So when I have a changing force, the way I deal with it in physics is I graph that force across a distance, and the area under that force line will be equal to the work done.